Hi. Now we will discuss about physiological principles in terms of biomedical engineering point of view. So first, let's discuss about systems approach. So we can consider human body as a system which requires inputs from outside for sustained operations and outputs. So converting food and air and water into energy and body mass for normal physiological function. So to understand our physiology in a systemic way, we define the concept of engineering system and system boundaries and the differences between open and closed system. Also here, we will discuss about the concepts of homeostasis and steady state, and we want to distinguish equilibrium from steady state. And the concept of a system or system approach is we define a system under our study or our defined boundary as a system. And then we consider about system balances in the context of systems physiology, including respiratory and gastrointestinal physiology. So let's talk about the mass balance. We all know that mass conservation concept, which is mass cannot be created or destroyed in general, except nuclear fusion or fission. So the concept of system as an engineering analysis, we want to define system boundaries. And that boundary means a physical sites of intersection between the system under the study and the rest of the world. So this is really dichotomous way of defining our interest as a system and the rest of the world. For example, we can define system as a human body, and kidney, or single cell. And when we define a system, we also consider the characters of the system as a closed system or open system. So that depends on whether we allow the system to exchange the matter with its environment. So for example, let me show one of the system conceptually. So this surface as a control surface, I mean, we have defined a controlled surface. So inside is our system, and that we call sometimes control variable. And outside is environment. In this case, when it's open system, there are materials or physical quantities can pass through, like this arrow shows. So that can enter, the matter can enter into the system, or the matter can go out of the system. So in this case, it's an open system, but there are closed systems which do not allow exchange of matter, which would be a much simpler case. So in an open system, we consider mass balance. So that open system allows exchange of mass across these system boundaries. Then we consider only about inside the system, how much of a mass will be accumulated or changing. So that's our main interest. Then let's think about what's possible in this system, how mass can be accumulated inside. So within the system, the rate of accumulation of mass inside system, let's put as ACC. And that accumulation can have various ways. First, let's think about through the system boundary, and there could be some mass getting into the system. If it's a human being, we drink, we intake food, and that can become this in, or the rate of flow of mass into our system. And also we can consider through the boundary out of the system. So that, for example, we urinate, and or this makes the mass from the system to the out of system. So that we define as an out. And also something we can consider is what if that particular mass can be created inside the system. Mass may not be the right case, but depending on what our interest is. For example, like heat can be generated within the system, or heat can be lost within the system. So that we put as a generation minus consumption. So generation or consumption is the rate of mass generation or consumption within the system. So this generation minus consumption means the overall net rate of mass production within the system boundaries. So this relationship really defines the mass balance with an open system, which will be used for our future analysis of a system. Before getting into a more analytical way, I want to define a flux. So flux is in Latin meaning flow. And this has been a useful concept, especially in transport phenomena, for example, like in fluid dynamics or mass transfer or heat transfer. And it's very simple. The meaning is the rate of flow of a property per unit area. So flux needs certain area for the property to pass through. So the quantity of flux is very simple. So the unit of the flux is the quantity of our interest per unit area per unit time. So it's a quantity per unit time per unit area. But sometimes some people do not consider the area as included in flux. So you gotta be careful in terms of context. So let me show an example of flux visualization. So let's consider an imaginary ring through which we are interested in how much of the quantity passes through. So for example, let's assume these arrows shows the photon of light. So if the same rings over here, and if the density of the light or photons are twice here, you can see with a given time, with a given area of the ring, there may be 3 photons pass, and here 6 photons pass. So flux is proportional to the density of flow. What if the imaginary ring is now oblique to the angle of the incoming this quantity, such as photon? So in this case, you can see from the distance between these arrows or photons, the density of photon are the same. However, this area become tilted that we can see while 4 photons pass through per unit time through this area, while here 6 photons passes through. So even if the density is the same, however, the boundary angle facing to direction of flow matters. So flux varies by how boundary this area faces with respect to the direction of the flow. And lastly, regarding to the area. So if the density of the photons are the same, if we have a different size of the area, we can see through this ring, there's only 3 photons, while this one 6 photons, assuming that this area is twice. So flux can be proportional to the area within the boundary. But this last one is a little problematic because I define flux as the quantity per unit time per unit area. So this one doesn't matches too much, but if we are interested how much of photons are passing through with through the ring, this is how we can think of. And in general, the quantities of our interest may be more general, such as it can have a vector field through the space, such as this. Then now the area or the surface orientation matters, which is described in the second part of here. So for example, let's say these are the vector field of fluid. The blue arrows show the distribution of fluid, And we are interested in the flux through a defined surface, which we define here as a green. Then at this surface, excuse me, the F, the original vector, tangential vector, which is represented as a yellow one, we can decompose it into a perpendicular component and tangential component. And think about this tangential component, which is parallel to the surface, so it never passes through the surface. So this component doesn't matter in terms of flux. So what matters in flux is that general flow directions normal component or perpendicular component contributes the actual passing through this surface. So only the perpendicular component and not tangential component contributes to flux. So keep this in mind. Now let's think about our body. So from engineering point of view, I defined the system as defined under the study. So how to define the system is upon us. So we can have multiple choices how to define system. Let's consider our body as a system. Then there are multiple choices. For example, so this is a drawing of the body, and you can see this gray one as a body and what's in and out of the body. For example, this is lung or respiratory system, then oxygen in and carbon dioxide out. And let's consider from the mouth to anus, this is called digestive tract or gastrointestinal tract. Then think about through the mouth, nutrient, salt, and water gets in. And through this digestion, we actually excrete unabsorbed matter and waste. Also, the other part is in this circulatory system, which collects oxygen and exchange oxygen and carbon dioxide. And through circulatory system, it provides through this renal system or kidney, giving the waste product. And through this, urine comes out. So organic waste, salt, and water can pass through. And so in this way, we can consider this as a system. But on the other hand, we can define our system really the epithelial layer of our body. Then technically this from the mouth to anus, that's digestive inside can be considered outside of the system. So that new definition is represented as a blue here. So we can define epithelial tissue as a system boundary. Then these are system, and inside the mouth to GI tract can be effectively considered as out of the system. For example, in the lung, this is lung alveoli, and that can be technically environment. Of course, in the kidney, this can be defined in this outside of the world. So there are ways to define system boundary under our study. And here, depending on that, the arrows represent the movement across the boundary. Once we define in this way, the GI tract, that exchange of, let's say, food molecules through inside the digestive system and out of this can become like considered, while in gray system, it doesn't matter. So really, how we define the system and system boundary can change the way we analyze the system